computing or quantum mechanics. My slide is not changing actually. I don't know. Hello?
Sir?
The slide was not moving. I don't know.
Okay. Sir, it is
Now
moving, sir. Yes.
yeah.
Okay.
Now the outline of presentation. First, I will give the basic motivation, and then quantum computing, qubit, and I will talk about the tensor product, which is used to extend the dimension, and quantum gates, quantum entanglement, Grover quantum algorithm, and application of Grover algorithm, and our work on the RC4, one of the oldest algorithm. After that, I will conclude and give the future direction. The motivation is why we need quantum mechanics. Since the classical mechanics is, there is some phenomena like black body radiation, photoelectric effect, and there is that young double slit experiment. These are the phenomena which people were not able to explain with the help of classical mechanics. So the people who developed the quantum mechanics, they were the topmost classical physicists. And experimentally, they found that what these phenomena cannot be explained with the help of classical mechanics. That's why the quantum mechanics birth took place. It is based on axiom-based development, and mostly all the axioms were experimental. You can't observe with the open eyes. Like if particle having weight less than 10 to the power minus 36 kg, where the classical mechanics is not applicable, they will apply the quantum mechanics. And why quantum computing is needed? There is some problem, complex problem that cannot be solved, that take more time with the classical computer, and quantum computer will be fast enough to solve that problem. One of the problem is the factorization algorithm. Factorization algorithm, which is a sub-exponential in classical computer, in quantum computer it become polynomial time, and searching algorithm is a problem which will which these two algorithm has impacted the cyber security. And if we use the quantum searching algorithm, key size will reduce by 2 in the metric key setting. And the motivation is it has a lot of application in artificial intelligence, machine learning, financial modeling, cyber security, digital banking means e-commerce, drug and chemical discovery, in battery technology, and Internet of Things, natural language processing, and logistic optimization. And just I will discuss the historical overview. What is the fundamental in quantum computing? The way we are representing the information. Some of you are aware of the representing of information in Avesca's quantum. That is, ball is representing the information. Avesca's computing will do 3 ball plus 4 ball will make it 5 ball. And those types of computing can be done with the help of Ohm's law. We have the serial circuit, supply the current with the I is equal to 1, then V is equal to IR, that R1 plus R2 plus R3, that will give the addition of that component, and that is because of the Ohm's law. This point is very important. And then voltage level information, like we are representing as of now, from 0 to 5 volt, it means 0 to 2.5 volt will be mapped to the 0, and 2.5 to 5 that will be mapped to the 1. And in quantum, we are representing with the help of spin actually. This spin up and spin down. What is the advantage? Here we have represent the information in the best possible way. The spin of the electron is representing the quantum information. If we have some more minor particle with With the help of that, if we represent the information and then process it, it will be the fast enough actually. Historical overview of cryptography. Caesar cipher was developed in around 50 BC, and Al-Kindi has broken that Caesar cipher, developed some method in 850 BC. Vinegar was in 1585. Kirchhoff principle was developed in 1883. Kirchhoff principle says every detail of algorithm is known to the adversary. Only the key is unknown. That means when we are discussing the cipher, every detail should be known and key should remain unknown. And Burnham cipher was developed in 1990. And quantum mechanics birth took place in 1925, but officially quantum mechanics was in 1920. Recently, in 2025, we celebrated the 100 year of quantum mechanics. Enigma was 1923. Shannon's coding theory paper was 1948, and Shannon's cryptography paper was 1949. That means coding theory is older than the cryptography. DES is one of the encryption algorithm. It is data encryption standard. It was standardized in 1975. Diffie-Hellman is the person where the scientific birth of asymmetric cryptography took place. That was in 1976. And the same year, the quantum information theory, which was developed by R.S. Ingram in 1976. This information theory is parallel to the Shannon's information theory, what he developed in 1949. These two are the parallel event, and RSA is 1978. RSA is Raver Samir Adilman, one of the public key algorithm which is used for encryption as well as signature. Maclis is 1978, and Samir secret sharing is 1979. Maclis is the code-based public key encryption, which is quantum safe. Richard Feynman is 1981, and BB84 is one of the quantum key distribution protocol. It was developed in 84. And Goldwasser zero knowledge protocol is 1985. Koblis and Miller elliptical cryptography was in 1986. Beham and Samir developed the differential cryptanalysis in 1991. Matsui linear cryptanalysis in 1994, and the hash function MD4 developed by the Rivers in 1990. This is a quantum algorithm. Source and Simon's algorithm was developed in 1994. SHA-1 was in 1995. Grover is 1996. The Cryptology Research Society of India. This is important society which take care of the proliferation of the cryptographic primitive cryptographic protocol, cryptographic research. It was in 2001, and in the same year 2001, AES was standardized, Advanced Encryption Standard. SHA-2 was in again 2001, and NESI completion was in 2003. This completion was to select some of the symmetric cryptographic primitive, basically the STEAM cipher, but none of them got finalized. And based on that, Adi Samir gave talk in Asia Crypt 2004 that STEAM cipher data live, and STEAM was after his talk, the people who started European Union started the E-Stream completion, which got concluded in 2008. And here we have some of the, like Grain is one of the finalists, Salsa is one of the finalists, and SHA-3 was in 2015. NIST PQC started in 2016, and Caesar completion concluded in 2018. Lightweight Cryptography 2022 and DPV Digital Privacy Data Protection Bill 2023. It is Government of India's bill. And NIST PQC in 13th August 2024, FIPS 203, 204, and 205. This is ML Module Learning KEM, Module Learning Signature, and this is hash-based digital signature. And one of the finalists from the code base like HQC This HQC family and the classic Michaelis family, these two are from same family. They are based on the coding theory. And recently, the next round in this, I think May 2026, the third round uh, for the additional colonist has announced, and out of that only less and cross the code-based digital signature been dropped, and uh, some of them is in the finalist. Still, that completion is going on. It will conclude within 2 years actually. The historical overview: what was the cryptography before 1900 when we don't have computing? Classical computing is there. We have the classical cryptography. When we have the quantum computing, we are having the quantum cryptography and post-quantum cryptography. Quantum cryptography is basically based on the no cloning theorem, and post-quantum cryptography is a classical cryptography only, but we are instantiating the problem which are hard enough to solve with the help of quantum computer. And DNA computing will lead to the DNA cryptography. That means the computing and cryptography are very dependent. They are not independent parameter. Once computing change, our cryptography has to be changed. And we can think of different types of computing and different types of cryptography has to come. Computing has a lot of impact on the cryptography. In this talk, we'll be talking about the post-quantum cryptography. That means we are building the cryptographic primitive which has to be resistant with respect to the quantum computer. And what is the quantum computer? Quantum computing is also universal computing, like classical computing is universal computing. Universal computing means given a well-defined problem, you can implement in that quantum Turing machine and the classical Turing machine. That means classical computer or quantum computer if it is a problem is well defined and well formulated. Quantum computing is a probabilistic, reversible, and have the quantum mechanics. What is the probabilistic means? Given input, output can change. Or your input remains same, but output can change. That is a probabilistic algorithm. And reversible means from input you can get the output. From output we can get the input. And it uses the quantum mechanics like superposition, entanglement, and these are too important for the computing. And classical started that early in 20th century. It took around almost half of the century to bring together the mathematics. Basically, when classical computer became practical in 1960s. And the quantum computer practicality yet to be established, and we hope that we'll have the quantum computer soon, which can be used to factorize the large composite number, and we can search the key size in AES-128 efficiently. Reversibility means this is not a gate. Here it is output is known, output is 0. That means input is 1. In not gate it is very well established. From the output we can guess the input. If output is 1, we know that not gate input is 0. If the output is 0, we know that input is 1. In the AND gate, if output is known, output is 0, 0, 0, 1. If output is 1, yes, we can say deterministically it is 1, 1. If output is 0, we don't have clue. Its input is 0, 0, 0, 1 or 1, 0. That means classical NAND gate is non-reversible. From output, we'll not able to guess the input. Similar thing applies. We can make it reversible. Reversible computing, we have x0, x1, x2, x0, x1. This is x2 XOR with x0 ended with x1. That possibility is there. We can have the reversibility of that computing. And classical computer works by processing data based on the sequence of 0 and 1. That means individual 0 or 1 bit is considered. And quantum computer uses quantum bit or qubit. That means it can be 0, R1, R0, and 1 simultaneously. It is the birthplace of the quantum computing. That is called the superposition. We can thought of like classical computer is once you toss the coin, it can flip to head or tail. But in quantum computing, we are doing spinning of the coin, which is can be head, tail, or can orient to any places. Qubit is represented by Dirac notation. The ket 0 is represented by 1 0 and ket 1 is represented by 0 1. We can have the superposition state ket psi is equal to alpha ket 0 plus beta ket 1. Here alpha beta are the complex numbers. Mod alpha square tells the probability of finding state in the ket 0 position. Mod beta square tells the probability of finding current state in the 1. And the fact the probability must sum to 1, so mod alpha square plus mod beta square is equal to 0. And a qubit can also be seen as a vector if your psi is equal to 1 by root 2 ket 0 plus square root 2 by 3 ket 1. This is a column vector. One dimensional qubit corresponds to the column vector which has two rows. Two-dimensional qubit will correspond to the column vector which will have the 4 rows. And three-dimensional qubit will correspond to the column vector which will have 8 rows. That means number of qubit to the power that if it is 1, it is to the power 1 in 3. If it is 2 to the power 2, that means 4 in 3. If it is 3, it is to the power 3, 8 in 3. And like we define the linear combination of the vector space, alpha 1 ket b1, alpha 2 ket b2, the linear combination of vector space resemble the similarity in the quantum computing that is called the superposition of the state. Tensor product is used to extend the dimension. That means we have one qubit which is of dimension n1 and the Hilbert space h1. Hilbert space is the space where your uh, qubits can lie each. They are belongs to the Hilbert space. Hilbert space is a vector space with defined inner product. And if H1 is Hilbert space of dimension n1, and H2 is Hilbert space of dimension n2, we can construct the higher dimension Hilbert space H by taking tensor product of H1 and H2. This is a standard technique to extend the dimension of qubit. Suppose we have one qubit system and one qubit system. We'll take the tensor product. We will have the two qubit system and dimension values. And the composite state is represented in the Hilbert space. In fact, all the states are in the Hilbert space. They have different application. If we have a column vector AB and column vector CD, we want to define the tensor product AB tensor CD. This is 2 row 1 column. This is also 2 row 1 column. So it will become 4 row 1 column. 2 cross 1 and 2 cross 1 become 4 cross 1 actually. That is very important. The quantum entanglement means two particles stated to entangle if they cannot be written as the product of two or one particle state. That is the if entanglement effect can be observed. If two particles are separated apart, any change happen in particle A, other particle B can also will get changed. It is if it is till end of universe or anywhere on the earth. This is used in communication protocol. We call it quantum teleportation. Is using the quantum entanglement. One of the important. One of the simple tests we can say the entanglement given a qubit. This is a qubit belongs to C4, this complex number. We have ABCD. If it is a separable, that means if AD is equal to BC, then they are separable. If it is not, it is not separable. The Bell state does not satisfy this condition. In this case, AD is not equal to BC, so Bell state is not separable. That means Bell state is an entangled state. And for higher dimension, we can have similar condition when become entangled. Mathematical representation of one-dimensional qubit, it is nothing but the column vector alpha beta. Alpha beta belongs to C mod alpha square plus mod beta square is equal to 1, represent the qubit. In the classical 0, 1 bit, we have already told this alpha beta is equal to alpha get 0 plus beta get 1. And how to take this qubit in the physical form? It can represent the polarization of photon or spin of the electron. Spin up correspond to get 1 and spin 0 correspond to get 0. We have already discussed in the beginning both technique, and there are some other technique to represent the actual qubit in the form of physical representation of that qubit, and we can process it. Like in vector space, we can change the basis. In qubit representation, we can also do the change of basis. Get plus is 1 by root 2, get 0 plus 1 by root 2, get 1. And get minus is 1 by root 2, get 0 minus 1 by root 2, get 1. Hadamard basis plus minus. This is called a Hadamard basis. If something, we have one-dimensional qubit, which is alpha get 0 plus beta get 1. This is same as alpha plus beta divided by root 2 get plus alpha minus beta divided by root 2 get minus. Measurement of the qubit. Measurement is done with respect to basis. If qubit is alpha get 0 plus beta get 1, measuring psi output either 0 or 1. The probability of outcome of get 0 is mod alpha square. Probability of outcome get 1 is mod beta square. And for higher dimensional, means two-dimensional qubit, we can construct with the help of two one-dimensional qubit. We have alpha get 0 plus beta get 1. This is the first qubit and this is the second qubit. We'll take the tensor product of these two qubit. We'll get the two-dimensional qubit, and the probability of outcome of get 0, 0 is the coefficient or amplitude corresponding to the get 0, 0. Probability of outcome of get 0, 1 which correspond to the amplitude of this alpha plus delta square. Output of probability of outcome of 1, 0. The coefficient of 1, 0 is beta lambda, so mod beta lambda square, and beta delta is a coefficient of get to 1, 1. And these has to satisfy that. Similarly, we can have another representation of two-dimensional qubit. We can say A00 get 00, A01 get 01, A11 get 1, A10 get 10, A11 get 11. And these coefficient also has to satisfy the condition. Mod 00, mod of A00 square plus mod of A01011 has to be 1. All these two qubit system cannot be written as the tensor product. That means this is two qubit system. If we are not able to we are not able to write in the form of two lower dimensional qubit, then that is the entangled state. Similarly, we can have three-dimensional qubit. In the case of three-dimensional qubit, the get 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1 will come, and corresponding we can write A0, A1, A2, A3, A4, A5, A6, A7. And these also has to satisfy that condition and multiple qubit system. Similarly, we can have n-dimensional qubit system whenever get 0, 0, 0, 1 and 1, 0, 0, 0. And last we have, this is the binary representation of all n bit number. Here when we talk about the three-dimensional qubit, we have the basis vector. In fact, they are the orthonormal basis 0, 0, 0, 0, 0, 1, 0, 1, 0, and they correspond to the 3-bit representation, 3-bit classical representation of the all possible, like 0, 0, 0 to 1, 1, 1. In case of n-bit representation, we have 0, 0, 1 to 1, 1, 1. So that possibility is there, and every coefficient, they call the amplitude, and mod of that has to satisfy this condition. And one of the important condition is the quantum state transformation, quantum computer. Already we discussed it is a reversible computing. That means their evolution is unitary evolution. Unitary evolution means there is a unitary matrix T which satisfies this condition. T into T dagger. Dagger is what? Transpose conjugate. Wherever the complex number is there, I, we have to change to minus I, and row will become column. This is means they are the inverse of each other. T is inverse of T dagger, or T dagger is inverse of T. That's why the reversibility of the quantum computing comes, and it is very important. If uh, energy is not preserved, then it is difficult to fill the quantum computing, and this condition will not be satisfied. After qubit, I will discuss the quantum gate. Till now, if you have any question and doubt, you can ask it. Am I audible?
Yes, sir.
Any
Yes, yes,
question
sir.
is there?
No issue, sir.
Okay, so I will start. That this is connected topic only, but totally. When initially we discussed the qubit, after qubit, we'll have the quantum gate. Quantum gate is basically used to evolve the quantum state. We have poly X, Y, Z gate. Poly X is nothing but it is a quantum NOT gate. And Y gate is the 0 minus I 0. If you see this gate is unitary, like we have discussed this condition. Unitary condition is a must. T into T dagger has to be identity. This gate also satisfy poly X gate satisfy the unitary condition, poly Y gate satisfy the unitary condition, poly Z gate also satisfy the unitary condition. X is a quantum NOT gate. This is similar to the classical NOT gate where ket 0 becomes ket 1 and ket 1 becomes 0. Z changes the relative phase of the superposition in the standard basis. When you want to change the phase, 0 remains same. 1, 1 to become minus 1. This is kind of complex conjugate. It's a relative phase. And Y, X, Y, Z, they are connected. Both are x square plus y square plus z square is equal to identity in fact. And xy is equal to iz and xz is equal to minus zx. They satisfy. That's why the poly xy z gate. This is used to develop the cryptographic algorithm. And 2-bit quantum gate is called the C0 gate. This is the CX gate. It is 0, 0, 0, 1, 1, 0, 1 transfer to that whenever A is 0, B will go as it is. If whatever the value of A is there, that will go as it is. If B remains 0, if B become 1, then only A will change. So this is the C0 gate used here. And it is the very important gate in quantum computing. Similarly, we have CC not gate, Hadamard gate. There are multiple gates which is used in quantum computing that we discuss in the cryptographic algorithm when we come to that place. After that, I will talk about the Grover search algorithm. It is used for searching a particular object of interest in the unsorted database containing an item, out of which just one item satisfies a given condition. Once the item is examined, it is possible to tell whether it satisfies the condition or not. However, there does not exist any sorting or database algorithm which we selected. The most efficient classical algorithm, suppose we have n object, we want to do the searching, we have to take one by one, one by one, one by one. That will take the order of n. Once we apply the quantum algorithm in the unsorted object, this on an average, the number of steps required is one. That means I am taking one object. Suppose first object itself become object of interest, I will continue. It is not, I will go for second object and keep it. This is the experiment with the replacement. We have the capital N ball. I'm taking one and then checking, and then second one I am taking to trial, and then I'm taking third one and fourth one. Finally, when I can get the object. In the worst case, the nth object will be the object of interest. So that means on an average, we need order of capital O of capital N step to get the correct object in the classical computing. If n is capital N is equal to the power small n, then the average number of steps for this order up to the power small n. What will happen in quantum computing? The law of Grover, 1996, he was a BTech student from IIT Delhi. He developed this. Now he is American citizen. Quantum algorithm for searching unsorted database that takes order of square root of n step in the quantum computer. That means classical computer will take order of n. Quantum computer will take order of square root of n step. So if n is equal to the power n, the complexity is order of to the power n by 2. We have the quadratic reduction. Grover algorithm is doing what actually fundamentally Grover algorithm do. Then we know the amplitude amplification. Grover search algorithm, it is in detail, it is like that abstract problem replacement. We have capital N object. Capital N is equal to the power small n state, which labeled S1, S2, Sn. These to the power n state are represented by n bit string. And we have the unique state SV, that is the state of that is the that is object in which I am interested. So C of SB is what? The object in which I am not interested. C of S is 0. Assume that for any state here, the condition C S is 0 can be evaluated in unit time. The problem is to identify the state SB. So what we'll do, initially we have to initialize all capital N state by equal amplitude 1 by square root of n, 1 by square root of n, 1 by square root of n, 1 by square root of n. There is a same amplitude for all n state. After that, it will enter into the quantum oracle. It will iterate square root of n time. Because of the iteration square root of n time, we are able to amplify the amplitude of the object of interest. Let the system be in any state S and Cs is equal to 1, will rotate by the phi radian. If it is a pi radian, means it's just reflecting that to the object. And if Cs is 0, leave the system unchanged. After that, we'll apply the diffusion transformation D, which is defined by the matrix as follows. Dij is equal to 2yn if I is not equal to Din. is equal to minus 1 plus 2 by 1. This diffusion transformation can be implemented as D is equal to h to the power tensor n. We have already discussed how to take the tensor product of the matrix, and R is the rotation matrix, and again tensor product of H. H is the Hadamard gate, which is used to create the equal superposition state, and Rij is 0 if I is not equal to 2. Rii is equal to 1 if I is equal to 0, and Ii is equal to minus 1 if I is not equal to 0. This is a rotation matrix. After that, after iterating uh, step 1 is just initial setup, and step 2A, 2B, and 3. That means step 2A and 2B will iterate square root of n time. After that, you perform the measurement with the object of interest. If it is a correct object, we will get with the probability at least half or more than. We can see the overall example of global algorithm. Here we have the tensor product of 0 qubit. It will apply an Hadamard gate. It will create the uniform superposition. And then this is a quantum oracle where we'll assign the state of interest to 1. For other state, it is 0. And then this is diffusion operator, whatever we have done in the step 2B actually. And this full thing will repeat by square root of n time. Then only it will have the amplitude amplification. We can see with the help of example. We have n is equal to 8, and the states are all 3-bit number 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And the object of interest is 1, 0, 0. That means whenever this will come, the CS will be 1. For other things, it will be 0. Prepare the 3-qubit system. That means your initial system is get 0, 0, 0. Get 0, 0 correspond to the 1, 0, 0, 0, 0. This is a get 0, 0. Get 0, 0 will apply the Hadamard gate. Tensor product 3 times. This is a Hadamard gate. Taken tensor product of 3 times. That means H, tensor H, tensor H. H is a 1 qubit gate having this is 2 cross 2 matrix. 2 cross 2 matrix multiplied by 2 cross 2 matrix and 2 cross 2 matrix. This is the 8 cross 8 matrix. And then we have the equal superposition state. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. We have created the equal superposition state. This corresponds to the first step. Initialize the system to the distribution 1 by root n, root capital N. What we have n here, capital N is 8. So we have 1 by root 8, all superposition state. This is the equal superposition state. Now we can visualize in the sensor graph all the state having equal amplitude. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 1. They are all of equal state. They have equal amplitude. Now, second step is step 2A. The oracle UW compute the function C on all the basis state for C of S is equal to. This is your object of interest. This become minus 1, 0, 0 is object of interest. That object of interest, it reflect the sign. Phase change, it become minus. Now again, that means if you see the graphically, amplitude remains same, just sign changes. Amplitude is 1 by root 8. This sign gets changed. Now it is a 2B step what we have discussed in the global algorithm. If you remember 2B, Dij is equal to 2 by n. This is the capital N. In our case, it will be 85 is not equal to 2, dii is equal to minus 1 plus 2 by n. The diffusion transformation D will satisfy this condition. This is the way how to implement that. Then we'll have the diffusion operator. What is happening here? Amplitude become 5. The object of interest. After applying the diffusion operator, the object of interest 100, its amplitude got increased. So it is become in the one iteration itself. Now in the second iteration, we do the same thing. Apply that state. That means to A will change the sign of the object of interest. It will become minus 5. That means it become minus 0.88 and then apply the diffusion operator. Diffusion operator here amplitude become 11. That means with a 94% probability, 94 point, this is amplitude. If we made the square, that become the amplitude. This is 97. With the help with the confidence of 97%, I can say this is my object of interest. So the same condition is we are working in the classical computer, classical searching algorithm. We will take order of n, means order of capital N. What here we did order of square root of capital N. That means square root of capital N, square root of 8 is between 2 and 3. So within 2 iterations, we are able to guess the. In fact, in the first iteration itself, we could get the clue which one is object of interest. But here, 88% confidence was there. To increase the level of confidence, we iterated one more time. So we get the 97% of confidence. That is good enough to say that yes, it is object of interest 100, which has the highest amplitude in the 2 iteration of global algorithm. This is the object of interest. This is our object of interest. Initially, we set up actually in the example. The 100 is the object of interest, and that become higher amplitude in the case of 2 iteration. And there are some examples with the matrix D, G matrix. The operator D can be expressed. So that we have already told. H to the power tensor n, R to the power tensor n, Hadamard transform matrix. That is to the power n is Hadamard transform matrix and R is the rotation matrix. The n-fold Hadamard operator in unitary and rotation matrix is also unitary. That we have already established. The condition of unitary is important. You want to any quantum algorithm, a quantum gate has to satisfy this. You want to do diagonal, T into T diagonal is to. After that, I will discuss the source algorithm. Source algorithm is a quantum computer. This is one of the important algorithms which has affected the asymmetric cryptography. Threat to the classical asymmetric cryptographic primitive invented in 1994 by American mathematician Peter Shor. Polynomial time quantum computing algorithm for integer matrices and used to solve discrete logarithm problems, RSA, DSA, Diffie-Hellman, ECC. ETC will get compromised, e-commerce and e-business will get affected thoroughly. This is the place where the PQC algorithm birth took place. The post-quantum cryptographic algorithms are algorithms which will, using the classical hardware in the presence of large quantum computer, they will survive. There is another important algorithm called the Salmon's algorithm. Salmon's algorithm using quantum computer. This is a threat to the classical symmetric cryptographic primitive invented in 1994 by Daniel Simon and this polynomial time algorithm for collision finding. For the same classical algorithms are exponential. The authenticated cipher used in, like we have the grain authenticated cipher that can be used to force the authentication type from the Simon. Grover with Simon can be used for structural attack on cryptographic primitive. That means we are using whatever the Grover algorithm we have discussed in detail with example and Simon's algorithm, which is used to force the authentication tag. Basically, when we are using symmetric cryptography algorithm, we have the confidentiality and integrity. Integrity can be forced with the help of Simon's algorithm, and confidentiality we can get when we can search the cryptographic key used for the encryption. Similarly, the Dust-Dozer algorithm and many other quantum algorithms that affect the classical cryptographic primitive, and one of the more important threat is stored to the decrypt model threat to the cover time of information. If we know the cover time of information, suppose we have information which has cover time of 10 years. Someone is started storing those information. Once he or she will get the quantum computer, that can be cover time will get compromised. So that is a very important. If the information which are having large cover time, for that we have to do the PQC migration. From classical algorithm, we have to shift toward the quantum algorithm, which are quantum safe. Either it is symmetric or asymmetric, both places still applicable. And quantum is very fascinating because of the quantum parallelism. This parallelism comes in two ways. This is called inner parallelism and outer parallelism. Inner parallelism, when we do the when we optimize the internal circuit, that means the circuit depth we have to do optimize, and outer parallelism is used when we optimize the number of when we try to reduce the number of qubit. If we are reducing the number of qubit, that is called outer parallelism. We are reducing the circuit depth, that is the inner parallelism. And this can be modeled with the help of that. Suppose we want to search the key space up to the power k, means key size is k bit. We have to apply the global oracle, which can have the cost of OG gate and depth is OD. And we have applied machine number of quantum computer we have to the power m. Then the key space get reduced to the power k minus m. This is the key. This key space is going to the one of the quantum computer. So that means that quantum computer will guess the correct key with the help of its square root of to the power k minus m. That means to the power k minus m by 2. It results with very high successful probability than the uh, that has the initial input. And same thing applies for other part, the circuit depth part. That OD is the circuit depth, this IM into OD will be the DM, and we have already discussed this is the to the power k minus m by 2 multiplied by OD. And finally, we'll have the GM is equal to pi by 4 divided by to the power k plus m by 2 into OG, the number of gate in the quantum numerical. With the help of that, we can use the quantum parallelism to reduce the number of qubit required and inner parallelism to reduce the circuit depth and resource estimation for the trick in 2016 when NIST started the competition. They have given the security level 1, 3, 5, 1, 2, 3, 4, 5, 6 and corresponding the circuit depth. If it is a security level 1 means it is equally hard to attack the AS128. Security level 2 means it is equally hard to attack SHA-3256. Security level 3 means it is AS192. Security level 4 means SHA-384. And security level 5, AS256. Security level 6 is SHA-512. And corresponding circuit depth is to the power uh, that max depth has a parameter between to the power 40, 60 and 96 to the power 40 to the power 60 and to the power 96 per max depth. The number of quantum gates will be to the power 170. And label 2, it is to the power 146 classical gate. Label 3 to the power 233 quantum gate per max depth are to the power 207 classical gate, and to the power 210 classical gate, to the power 298 max depth quantum gate, and to the power 272 classical gate in that sense. And label 6, it is also known as paranoid security. And this is basically the key recovery attack with respect to AES and SHA 3 to, in case of SHA, it is to attack the cryptographic collision hash, that to find the collision in the hash function. This table was given by NIST when they have called for proposal. They wanted the people who are submitting cryptographic algorithm, they have to give these types of security level classification. If the public key has security level 1, then it has to have to the power 170 quantum gate per max depth. If a public key security level 5, it should have to the power 298 quantum gate per max depth. But because of the research evolution, they have updated the table. Now AES 128, they have updated the table in 2022. AES 128 is means level 1 security will come to the power 157. Initially it was to the power 170. Now there is a reduction. Classical remains same to the power 146. Then since there is no change in the classical algorithm which can find a collision in hash function, but there are the optimized implementation where they have done the inner parallel, means they have done the concept of quantum parallelism where people can reduce the number of quantum gate. Here reduction was when the plain implementation it had to the power 170 quantum gate, optimized implementation had to the power 157 quantum gate, and similar optimization for 192, PS 192 and PS 256. It is the change actually. Initially it was 298, now it become 285. Classical gate remains same. What is the max depth? If max depth is to the power 40, that means approximate number of logic gate that presently envisage quantum computing architecture are expected to be serially performed in here. That means if you have the quantum circuit which has the max depth up to the power 40, any computation which enter the circuit and it will come out of that circuit, it will take 1 year of time. If your max depth to the power 46, it will take 10-year time to compute the output. If it is to the power 96, then it will take the 1,000 year of time to the compute that. Based on that, NIST has decided if you want the cover time of more than 10 years, we should use the cryptographic algorithm of level 6. This corresponds to the cover time of 1 year, level 1, and level 5 is around cover time of 10 years, and more than 10-year cover time. The cryptographic algorithm has to choose it from the level 6. And what is the circuit depth? If you see, this is one of the quantum circuit. Here we are operating gate 0, 0, 0. This is Hadamard gate. This Hadamard gate is used to create the equal superposition, and it is the 1 qubit gate. And here also Hadamard gate is there. This is a C0 gate. This also C0 gate. This is a T gate. This is a T gate. And this is a C0 gate from qubit 3 to qubit 2, and qubit 1 to qubit 2, it is C0 gate, and HHS, this is Hadamard gate, and then S gate. We'll get the state size. Then this is called the circuit depth. That means if we compute, you start from the input, go toward the output. What is the quantum gates are there? You see, the T depth is 1. In this leg, we are using 1 T gate. In the second row, also 1 T gate is there. And what is the H depth? H depth, if you take a row, a leg starting from left to right, maximum number of H get used. if we see the first row, maximum number of edge gate is used 2. In the second row, maximum number of edge gate is used 1. In the third row, maximum number of edge gate is used 2. So edge depth is 2. If we want to compute the full volume, how many gates are used, then we have to count all gates. We have one S gate and 3, 4, 5 H gate, 2 T gate, and 1, 2, 3, 4 C naught gate. So that means 4 plus 5 plus 2 plus 1. This is the total number of gates. That is called the volume of the circuit. Volume of circuit become important when we consider qubit and the gate used in that operation. And once we have the volume, we can compute the how many gate and how many qubits are used in the circuit. We had done some work on the RC4. RC4 is one of the important algorithm. It was used in the almost 20 years. It was used in the e-commerce domain. Now they are changing with the new algorithm that is called the Chacha. And under the Grover's lane, RC4 is widely used as well. Enumerate the quantum resource required to perform the exhaustive research attack on the RC4. We demonstrated that RC4 is not fit for level 1, level 3, level 5, and potential of quantum computing revealed in the quantum cryptanalysis. The cost of global search. If you want to have the global search algorithm on RC4, global search means if you remember the circuit, whatever we have shown here, this is a global search algorithm. Key size is a k bit. Then we have to iterate this algorithm by to the square root of to the power k. That means square root of to the power k means to the power k by 2. Within half, we can get the correct output. So in case of max depth to the power 40, it's recommended it should have number of quantum gate in the global search algorithm. Global search algorithm to the power 258, and if your max depth is to the power 64, number of quantum gates should be to the power 30 to the power 234. If max depth is 96, the number of gates should be to the power 202. In our study, we found that RC4 is having to the power 245 gate in the case of max depth to the power 40, and it had to the power 221 gate in the case of max depth to the power 64, and it had to the power 189 gate quantum gate in when max depth to the power 96. That means RC4 is not safe to use for 1 year cover time. If it is not safe for 1 year cover time, definitely it is not going to use for 10-year cover time, and it is not going to use for the 100 means more than 10-year cover time. So that's why maybe the people has removed the RC4 and they have selected new symmetric decipher called Chacha. What is the impact on cyber security? If you remember, the security of symmetric cryptographic algorithms are reduced by 2. That means the AS128 will be 64-bit security in quantum era. The winning of key size is needed. AS256 will have 128-bit security in quantum era. For 256-bit security in quantum era with AS, we have to change the structure of the algorithm. That means AS is not designed to, if you want to 256-bit security, that means we have to have 512-bit key. But AES is designed to have key size of 128, 192, and 256. If AES is used with key size up to 56 bit, that means it will give the quantum security of 128. That become half because of the proper algorithm. AES 128 is used. It will give the quantum security of 64 bit. AES 256 will have the quantum security of 128. If you want the quantum security up to 56 bit, we have to do the structural change in algorithm. And the new design with many use of that we have to use the key size larger than 512 bit is very much needed. After that, I will conclude the talk. We have discussed the qubit and basic motivation for the quantum computing. And quantum gate. Quantum gate is also unitary matrices. Quantum gate for 1 qubit, quantum gate for 2 qubit. Quantum gate can have 3 qubit also. They call the CC naught gate. That is the roughly gate. And future direction where we have to move. Basically, the RSA was using one set with one operation. DPA one is also one set with one operation. We have we have changed from set to one set having two binary operations like vector space, ring, or module types of things. Basically, this is a post-quantum era. Classical computing, we had the group, maybe additive group or multiplicative group with on which we have developed the RSA, algorithm, and other subset symbols. But in the future, when quantum safe era, we have one set with three operations that we call the ring module and vector space. If we have to have developed more cryptographic algorithms which are going to save with respect to the DNA computing and all, we should think towards having one set with three operations, O1, O2, O3, like heap and thrust we have. These three operations are also binary operation. If this O3 become identity, then this become B O1, O2. If O2 and O3 both are identity, then we'll reach here. So that means it is the higher dimension algebra where we have the three binary operation, something similar what they call the heap and thrust. We can use to develop this type of algorithm. Design of PQC algorithm and quantum resource estimation is one of the important research topic. Choose a cryptographic algorithm and estimate the quantum resource when it is attacked with the help of global algorithm. Like for the RC4 we have done, and similarly people can do for some other cipher, the cipher of interest. They can choose, and then finally, if you estimate that quantum resource, we'll able to know that it is quantum safe or not. That algorithm can be used, or we can use, or how long we can use, what is the cover time of that information. Design of quantum safe cryptographic algorithm. This is for the symmetric key cryptography as well as public key cryptography. Both cases it is true. New quantum algorithm is equal to quantum search. Suppose we have the quantum search algorithm, like we have discussed the Grover algorithm, and we have any other algorithm where we can use the Grover search algorithm. That means we already have one algorithm and we got the opportunity to use the Grover algorithm in that algorithm. The new algorithm will be more efficient than any other quantum algorithm. So Grover is very fundamental algorithm and it can be used to find the improve the other cryptographic algorithm or other quantum computing algorithm, and it will help a lot. With this, I conclude my talk. If you have any question, you can ask. Thank you for your attention, and most of the reference were from our book, what we recently wrote, Quantum Algorithm and their application in cryptology, a practical approach. It was published recently with the CRC Press, and So most of the 90% material will taken from this only. Yeah. If you have any question, you can ask actually. I'm done.
Sir, thank you very much, sir, for your valuable insights. So I have a question. Sir, how to test this quantum cryptographic algorithms, as there is no real quantum computer so far? I mean, maybe IBM or recent quantum computers are like in a real, but most of the cases we work with the simulators only. As far as simulator concerned, I think there is there is no mirror, then we could not get a proper kind of result. So how do we proceed further as a research community? How you people are working, because you got several case studies, but we from the academic research side, therefore we wanted to continue. Then could you please give us some glimpse so that we may maybe extended somehow further?
Yeah. Uh, Hello.
Yes, sir.
Am I audible?
Yes, sir.
Uh, as of now, we don't have any practical quantum computer which can simulate searching of the key. But we do have resource estimation technique. We'll implement the small case with it is like we calculated the resource estimation in RC4. That paper is also available. For the small case, we'll calculate and then interpolate for the larger key size. Suppose for 4-bit key size, we have calculated the resource. And then if I want to calculate for 8-bit, I will multiply by 2. That is the way people do estimate. And these estimation may not stand when we have actual practical quantum computer. It may change. As of now, we are doing, this is the theoretical estimation. I'm expecting that theoretical estimation will be the best estimation. Whatever practical quantum computer going to come, they will have more, they will need much more resource than this actually.
Sir,
So research should continue. We should not wait for quantum computer to come.
sir,
Theoretical analysis, at least the small scale implementation we can do with Qiskit or whatever simulator we have. India has a QC, what CDEC and IT Roorkee had developed. Over that we can simulate a small scale and interpolate for the larger size. That is
sir.
the question. Yeah.
Yes, sir. Thank you very much, sir, for your valuable time. And despite
Yeah.
your busy schedule, so it is very hard. I thought of hosting you all offline, but it is my unfortunate we couldn't make it. So for the next time, I think we hope you should be present here for the next event, hopefully. So thank you very much, sir. And
There is one question in the chat box, I think. Can you share idea on hot research idea in the area of quantum computing with cybersecurity or quantum computing with network? What is the hot research? I don't know who has typed from name in there. Have you read that question?
Thank you.
Rijul Prakash. Okay. No, basically nowadays we are talking about the quantum network. That there is like we discussed the BB84 protocol. BB80 protocol is it one to one. It is when we go for the quantum network, that is a challenging actually. How to have one to many or many to one. Both possibilities are not there. We can develop some quantum network protocol which sustain from one to many and many to one. That is the hot research topic actually. You can start from there. Still quantum communication or quantum internet or quantum network is it one to one. Till now, no one had developed one to many or many to one network. That is a important research topic in the quantum network. I think I am done. Any other question?
No, sir. Thank you so much, sir. As we come to the conclusion of this enlightenment session, it is privilege to propose the vote of thanks on behalf of the Gayatri Vidya Parishad College of Engineering for Women and organizing team of ANRF funded 5-day faculty development program. So we sincerely thank you for sharing your valuable knowledge and enrich experience with us. Your insightful presentation on quantum computing, cryptography, and quantum safe security technologies has provided us with a deeper understanding of one of the most transformative technologies of our time. Your discussion on cutting edge research, practical challenges, and future directions in the quantum technology has been both inspiring and thought provoking. We are especially grateful for the clarity with which you explained complex concepts and the highlighting India's advancements and contributions in the field of cybersecurity, cryptography, and the quantum computing. My heartfelt thanks to go to all the participants for their enthusiastic involvement, active interactions, and keen interest throughout the session. Thank you so much, all of you. Thank you, sir.
Yeah, thank you. Thanks a lot. I will leave the meeting. I'm within time actually. I completed 4 minutes before the 5 o'clock. Thank
Sure.
you.
Thank you, sir.
Thank you. Thanks again.
Dear participants, online and offline, tomorrow's session will start sharp at 9:30 a.m. Please be present.